Okay, hi everyone. We are happy to have Hamza Ahmed from Northeastern. He will talk to us about the twist on heterotic little string dualities. Please start.
Thank you. So thank you, first of all, to the staff for having me speak here. Hello, everyone. I'm Hamza. Today, I'll talk to you about some work that I've been doing for the past year and a half or so, which is basically resulted in these two papers with Paul Constantine Ullman, who was a postdoc at Northeastern and is now at UCSB, and my PhD advisor, Fabian Rula. So broadly today, I'll tell you about the heterotic little string dualities, and in particular, their T-dualities. And I'll explain what that means in a second. And sort of the landscape of these T-dual theories, more specifically in the context where we allow certain extra data, which in this case would be certain twists that, again, I will introduce in due time. But before we get to that, let me sort of just motivate. Is there a question?
No.
So before that, let me just sort of motivate why little string theories in general are an interesting class of theories. So we know that quantum field theories have global symmetries, which obviously tell us a lot about these theories. And in recent years, well, now about 10 years, we've realized that this global symmetry structure is even richer, and we have what are known as generalized symmetries or higher form symmetries. On the other hand, in theories of gravity, insofar as we think string theory tells us something universal about gravity, we know that this no global symmetries conjecture, where we think that theories that are coupled to gravity shouldn't really have global symmetries, but string theory has told us that these theories have another interesting property, which is known as T-duality, which is basically the statement that if you have two theories which are distinct in some dimension d, and the statement of T-duality is then that these theories may be equivalent once you compactify down to some lower dimension. So they may be equivalent in, say, d minus k dimensions. So inequivalent theories in higher dimensions, equivalent theories in lower dimensions. So then one can ask if there are theories that admit both of these properties, the property of T-duality and global symmetries. And so, spoiler, indeed, these are the theories that we will study today, which are the six-dimensional supersymmetric theories known as little string theories. And so, in particular, these theories form this nice middle ground between full-fledged like quantum field theories with global symmetries and gravity theories. And so that makes them an interesting class of theories to study. In particular, the global symmetries that we will be interested in our work here, or in this talk today, will be what are known as two group symmetries, which I will explain a little bit more later on, and the conventional zero-form flavor symmetries. On the other hand, what I will mean by T-duality will be, as I said earlier, but we'll stick to circle compactifications. So I will take two 6D little string theories, which are distinct in 6D, and then I will put both of them on a circle, maybe switch on certain data along the circle, some holonomies or something. And then the claim is that T-dual theories would lead to the same 5D supersymmetric theory. So the way I like to think of those string theories is that they're special quantum field theories with this additional property of T-duality. So in particular, you can sort of use this T-duality to sort of look at the theory in a frame where its description is simpler. And so
Sorry, can I ask the same 5D theory, does that refer to a low energy limit going to 5 dimensions? So I usually thought of T-duality as something that was true at finite size of the circle, not in the limit where I think of the circle as small.
Yeah. So I would say that this would be a statement about the equivalence of the moduli space, of the 5D moduli space. So one of the conditions I'll show you would be sort of the dimension of the Coulomb branch in 5D is the same. So I don't think you need to take the circle to zero size. But for us, what will be important will be to keep all the KK modes. So it's not like we'll integrate out and go to some low energy limit.
Okay.
Cool. Thank you for the question. So yeah, so what we will consider is this question about the structure of this map. So what does this landscape of T-dual theories look like? And the other question that's interesting is, are there any invariants that one can identify on both sides of any candidate dual theories and show that these must be invariant for T-dual theories. As we just sort of talked about, one of them will be the 5D Coulomb branch, which I'll explain a bit later. So, right. So before we get into it, let me sort of give a very simple outline of this talk. So I'll first review what little string theories are from a purely field theoretic standpoint. Then I'll explain the specific kind of little string theories we'll be interested in, which are known as these heterotic little string theories. Then I'll explain sort of what it means for LSTs to be T-dual. And then if you have time, we'll get into the result section of the talk, where sort of I'll explain what this twisted T-dual landscape is and how we can use sort of these new techniques here to write down a completely new class of little string theories that were not known before. And then I'll give a brief outlook with some future directions. So what are little string theories? So the kind of little string theories we'll be interested in will be minimally supersymmetric. So then in 6D, you have either 16 supercharges or 8 supercharges. So we'll consider, as it turns out, the more richer class of theories comes from minimally supersymmetric little string theories. So before I get to those, let me sort of just review minimally supersymmetric 6D quantum field theories in general. So like I said, these are just 6D supersymmetric gauge theories with with 8 little supercharges. The gauge algebra is some product of these gauge algebra factors. And yeah, so throughout this talk, I'll just mention I'll focus on the algebra and not the full group. And that's what's relevant for what we're doing. But it is obviously an interesting question to see how what we're doing generalizes once you or extends once you include the full gauge group. So let me sort of start by just giving you the representation of the supersymmetry algebra in 6D. So you have the vector representation, you have the hypers, and you have the tensors. And these tensors are precisely what lead to these exotic, I would say, things that happen in 6D. And so note that the important thing for the tensor multiplet are these scalars phi and this anti-symmetric two-form B field, which is not something you usually find. Well, you do, but like in lower dimensions, right. So the point is that you can't just pick any number of vector multiplets, hypermultiplets, and tensor multiplets and expect a consistent theory, because note that this is a chiral theory. It's 1,0 SUSY. So you have chiral anomalies, which need to be canceled. And so these anomaly cancellation conditions in 6 dimensions restrict what vector multiplets, hypermultiplets, and tensor, what number of of these multiplets you can have. So this, in addition to the supersymmetric algebra and these gauge algebras, constrains the 6D theories that you can have. Now, of course, you can have gravity added to the mix, so you can couple this to the supergravity multiplet, but we will only be considering supersymmetric gauge theories, so we won't couple to gravity. Right. So now, if you have such a minimally supersymmetric theory with some number of tensor multiplets, so indeed you need to have at least one, then you have these BPS strings in the spectrum, which you know, a string naturally couples to these B fields in the tensor multiplets, and this coupling leads to these BPS strings then have what's known as a Dirac pairing matrix is associated to them. So you can think of this pairing matrix as the analog of what we have in 4D for monopoles and electrically charged particles, the Dirac quantization. But this is in 6D, you have the same thing, but you have it for strings. And it turns out that the determinant of this matrix actually determines the UV completion of your 6D theory. And let me sort of give you some intuition for why this is true. So we know that in gauge theories greater than in dimensions greater than 4, the gauge coupling is non-renormalizable. So in particular, these theories are not well defined in the UV. But in 6D, there's these tensor multiplets sort of cure this sickness. What happens is that sort of because of the supersymmetry, the gauge coupling is related to the tension of these strings by an inverse relation. So what happens is as you go to high enough energies, when the gauge coupling becomes very large, at the same time there are these BPS strings that are becoming tensionless. So at the very high energy limit, these new tensionless strings provide you with these degrees of freedom, new degrees of freedom that then UV complete your theory, which is precisely why you can UV complete your 6D supersymmetric quantum. There are these UV fixed points for 6D supersymmetric quantum field theories.
So these BPS strings, they're on the Coulomb branch of the theory only, or?
Yeah, so they will be on the tensor branch. In 6D, you have
the tensor branch,
yeah, you have the tensor branch, exactly. Yes, exactly. Yeah. Good. So yeah, so in this case, so there are 3 kinds of UV completions that you can have. In one case, you include the gravity multiplet. So as you can see, there are these 3 values of the determinant. And of course, for the first 2, the supersymmetric, the supersymmetric conformal, the superconformal field theory, and the little string theory, where the gravity multiplet is decoupled. And the third one is just the supergravity theory, where of course you have the gravity multiplet. And so, of course, the important theory, the important class for us is this middle column here, where note the determinant of the matrix is 0. So that means that there's a 0 eigenvalue, which, as I'll show in the next slide, is very important because this is what leads to the higher form symmetries that I sort of mentioned earlier.
Why? How does if I think about just the 2-0 case with double the supersymmetry, its UV completion is a superconformal field theory, which in turn is a limit of a little string theory. Right. So I mean, there's a hierarchy of scales. Why? Here you're saying the determinant. I mean, there's no little string theory in the first column at all at sufficiently high energies. Can't I hold M string finite?
So in the first, yeah, I see what you mean. So you're saying that in the 2,0 case, you have obviously the world volume theory of the M5 brane, and there the IR limit is the SCFT, is the 62,0 SCFT. But no, these are both UV fixed points. So the LST here and the SCFT are 60 UV fixed points. So there, the IR limit of your 62,0 LST is the 62,0 SCFT, right?
That I can still view as a fixed point for the Coulomb branch theory, or the tensor branch theory, whatever you want to call it. Just like in else, there's a UV completion of the abelianized theory on the Coulomb branch. I'm a little confused how there can be a difference between these first two. Like, oh, maybe you can explain it when you tell us why the determinant matters.
I mean, it's like shrinkability, like in an ICFT,
Yeah.
you have shrinkable curves. For
Yes.
LST, you get a self-intersection 0.
Yeah.
So they're shrinkable at infinite distance, gravity is the same.
Say that too fast. I didn't understand.
I think from the geometry,
If you-
yeah, that's what happens. But I think from the field theory, I'm trying to think why.
I mean, M little string theory is a scale that in principle has nothing to do with whether or not there's a IR CFT.
Does the center of mass decouple when you take out the field theory limit? The T-duality require the center of mass for the M5 branes?
Yeah, sorry, could you repeat that?
I asked if the T-duality for the M5 brane little string theory requires the center of mass, or can it be done without the center of mass?
I think it should, because yeah, it does, because of the, like you said, the T-duality. Yeah, I guess at this point the only difference I see is that it's like the UV complete theory in 6T in its 16 supercharges is the little string theory. Once you integrate out these massive modes, then you get in the IR and SCFT.
No, but Sav is discussing the fact that there is a little string theory which can flow to a SCFT. And we're discussing how there's many such examples of that. The M5 brane is one example, and we're trying to figure out how the determinant changes from 0 to positive in that. And I guess my hypothesis is that it involves a decoupling of one of the tensor multiplets.
Yes, exactly. Yeah, it would. Yeah, no, sorry. Now I understand. I apologize. Yeah, you make one of the strings really massive and it decouples. Yes.
Like
So
this 0.
here you would kick out one of the strings.
In particular, the null eigenvector of the determinant is the one that decouples.
Mhm.
Yeah.
Good, that makes sense. I see. And you're saying that in the supergravity case, there's no. Oh, what you call the supergravity case has. How do you tell?
Yeah, so with the supergravity, it's kind of. I mean, I must admit, I don't know exactly how they get this -1, but it has
So
to.
it has a tensor with an opposite signature, right?
Yeah, it does have. Yeah, from
So
the.
I think that's closely related to that -1.
Yeah, but
Sugra multiplet, if the tensors are self-dual for the field theory by convention, then the Sugra multiplet will have the opposite duality
Yeah,
condition.
but why it's fixed to -1 is, I think, related to this.
It's because it's in the gravity multiplet.
The signature of the lattice is like 1 minus 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 minus, so it depends on how many tensors.
Yeah, it has. Yeah.
So it couldn't consistently be -2 because you'd have two
I think that implies
opposite signs.
I think that means you have two opposite signs. Yeah.
I think in supergravity, it refers to the whole lattice, not just like the anomaly lattice that is
Yeah.
embedded in the full lattice.
So as far as I know, this has to do something with diffeomorphism invariance as well. So this fixes it to -1 with diffeomorphism invariance. This is in this old paper by in the LST classification paper by in F theory, 2016 paper, I think. Yeah. Cool. More questions, or should I? All right. Right. So now there's a nice description of these theories, which was sort of already alluded to on what's known as on the tensor branch of the theory. So we can preserve supersymmetry and while giving vebs to these scalars in the tensor multiplets, which takes us onto the tensor branch of the theory, where all these strings that I talked about are tensionful. So they're not tensionless anymore, and so this can be represented as a quiver gauge theory here, where you have these gauge algebras here, which I mentioned earlier, the gauge algebras of the theory, and then you have these strings underneath them. So these are the BPS strings from earlier, which are labeled by their self-direct pairing. And then you have implicitly some bifundamental matter between these gauge algebras, which needs to be there, remember, to satisfy the 16 anomaly cancellation. And then you have some flavor symmetries potentially. And so now, so this is obviously true just for both the SCFT and the little string theory and the supergravity theory once you go into the tensor branch. But the fact that this eta has a 0 eigenvalue for the LST leads to something qualitatively different in the theory, which is the existence of a non-dynamical two-form field in the theory, which couples to what is colloquially known as the little string. And so the reason that this happens is because these etas also by supersymmetry are the kinetic term, are the coefficients of the kinetic terms of the B fields. And so if the matrix has a 0 eigenvalue, then you can always go to a basis where one linear combination, the kinetic term of one linear combination vanishes. And so that particular B field is no longer, it's not a dynamical field of the theory. So it's a non-dynamical two-form field, background two-form field that's been coupled to the theory. And so this now generates what's known as a U1 global one-form symmetry of the theory. And so this adds to the global symmetry data of the theory, which is not a part of the SCFT and obviously not a part of the supergravity theory. And these are what are known as this particular linear combination, which is the combination that vanishes, the coefficients of this linear combination are what are known as the little string charges.
So this is basically the same. This is what you were saying. Basically, it's the same as taking n equal 4 Yang-Mills or something like that, going to the Coulomb branch, and then the U1 factor will freeze out, and you're
and
it's not asymptotically free. And sorry, you say n equal 2 with UN and some charge matter, where the U1 is coupled to the charge matter. We'll just decouple at low energies.
Well, here this one doesn't decouple in the sense that it's not dynamical, but things can still carry charge under it.
No, but it would be the same way for UN plus charge matter.
Sure. Yeah. It's not, it doesn't propagate, but things can still carry charge under it.
Exactly. Yeah.
Good.
Okay, good.
Yeah. The point is to distinguish the little string case from the CFT case. Yeah. In the little string case, there is such a thing as the string charge, which is well defined in the theory. Strings carry this charge. In the CFT case, you might think that there's something like that by looking at the tensor branch, but when you actually go to the fixed point, there is no such charge.
This exists also for the gravitational ones?
No, no. Supergravity theory would not have a global symmetry. It would somehow be gauged or it would be broken.
This would be dynamical in that example. But in this case, it's a global background field. It's not propagating. In the gravity case, it would propagate.
Yeah.
Yeah, precisely. Yeah, and you would see this at the level of the current algebra, for example, this two-form field. Good.
I see. Okay. Sorry, go ahead.
Yeah, no, good, very good questions. So, all right. So now that I've sort of reviewed little string theories, in general, let me sort of focus on the particular kind of little string theories that we'll focus on, which are the heterotic LSTs. So as the name suggests, these are associated to the heterotic strings. And so we have each of the two kinds of heterotic strings here. So the E8 times E8 LST and the SO32 LST. So let me sort of describe what these are. So now we'll sort of switch gears a bit to more stringy stuff. So so in the E8 times E8 heterotic LST, we know that we have NS5 branes. And these theories are essentially the world volume theories of a stack of NS5 branes, these LSTs. And in particular, the transfer space can be pretty rich. In particular, it can be this orbifold singularity, which defines, as I'll explain on the slide later on, the singularity type of your LST. So this is another piece of data that defines your E8 times E8 heterotic LST. And finally, there's this choice. You have additionally a choice for the flat connection for the E8 times E8 bundle. at the boundaries of this C2 Mont gamma G space. And in particular, this choice is encoded in a group homomorphism, which is given here, which is from the first fundamental group into the E8. But I mean, this isn't important for us too much, but because from the physics point of view, all this is doing is that it's picking for you the flavor symmetry of your Volt volume theory. So the flavor symmetry of your LST. So if I pick a trivial flat connection, then I will have the full E8 times E8 flavor symmetry. If I pick some non-trivial flat connection, some non-trivial embedding here, then I would break the E8 times E8. And we will see this in explicit examples. Another way to represent these theories, another interesting way to represent these theories is via the Horzhava-Witten picture in M theory. So we use the heterotic M theory duality, and let's say for trivial flat connections, we have the following picture. So we have now, obviously, the NS5 branes and the strong coupling limit go to M5 branes. And then they can be certain M2 branes that stretch between the M5 branes, which are essentially the strings of the LST. And then if you bring the M5 branes on top of each other, you are at the LST fixed point. And then you also have these E8 factors realized on the M9 branes. And so in the quiver notation that I introduced earlier, this is the theory that you get. So you have these, remember the square brackets are the flavors, you have these E8 times E8 flavor symmetries, and then the singularity G, you have the singularity G on top of each of these strings. So the 1, 2, 2, 1 configuration is what you get in this case. This is not the full tensor branch. So this is what's known as the partial tensor branch of the theory. And this partial tensor branch is the same for any E8 times E8 LST. However, if you want to write down the full tensor branch, that actually depends on what your singularity is. So for the experts, in particular for the expert, I mean, from the geometry point of view, what you have to do is you have to add conformal matter, GG conformal matter pieces between each of them. But in general, as we'll see in the examples, in examples later on, is that just the curve configuration changes when you go onto the full tensor branch, depending on what your singularity type is. So that bit is not fixed by
Question?
Yes.
How does gravity decouple for the LST in this case?
Oh yeah, so good. So well, first of all, you're probing a non-compact space. So
no, yes, but in the Horzhava-Witten picture, you just have like if I was gonna have just an E string, then I could just send one of the M9 branes to infinity and then decouple the lower dimensional M Planck.
Yeah,
but
yeah.
In the little string theory, you're keeping all of them. So
Yeah, in the little string theory, I'm keeping I'm keeping one scale fixed, right? I'm keeping there's a linear combination of these M2 branes whose tension I'm keeping fixed.
how do I see that the lower dimensional Planck decoupled, that gravity is no longer?
Yeah, from the Horzhava-Witten picture. Yeah, that's so here I know I'm probing the C2 Mont gamma G. Oh, I mean here also, I mean, I guess this is how you can see it, right? So the M5, sorry,
Sav.
No, I think, isn't the interval size going to 0?
No, but then you're making them Planck. No, usually, I mean, if you want to probe an E string, then you just put in an M5, and then there's a string stretch, and you can send the other M9 to infinity, and then it kind of becomes like it's global symmetry and the lower dimension M Planck.
Yeah, I mean, this is what's happening. These M9s are at infinity. This is why this is a flavor symmetry for the M5 brane, right?
It happened to be at infinity.
Didn't both circle?
Sorry, this is in E8 heterotic, right? So don't you take G string to 0?
Yeah, the G string is sent to 0, yeah, because gravity is decoupled, yes.
Right, but that's the interval size going to 0.
Yes.
No.
Yeah, I think so.
Yeah, but that would be
I mean,
Lower dimension and Planck is R times the higher dimension.
Yeah. It's not exactly G string, like you say. Yeah, it's
you think that you're taking M Planck higher to infinity, R to 0, holding fixed M string in 10 dimensions, and G string is going to 0. M string is just scale.
This
These are
picture
all
is
strings.
no G string.
No, there is G string, it's interval size.
But I'm saying you don't need it. The interval size, yeah, I'm just saying you can directly name it.
so I
And
mean,
higher dimension and Planck will be fixed if I just do it.
so if I have a heterotic theory where I decouple gravity, I still can take the strong coupling limit to
No, I don't think you can do that. If you're decoupling gravity, you're taking. It
You're
depends what
using
you
it to
mean by
decouple gravity on the 5 branes.
on the 5 by taking G string to 0, right? That's you want a whole fixed M string if you want a little string
But
theory.
to do that, then you have to send the two M9 branes to infinity, right? While
No,
keeping the overlapping M5 branes fixed.
What's infinity? To
To decouple the Planck on.
no, that's the 11-dimensional. This is a 10-dimensional string theory at the end, right? Actually, I'm not sure why you have a Java-Witten picture for this at
No,
all.
this is 6D theory.
No.
Well, I mean, I can always. Well, I mean, the NS5 brain. Like, I see what you. Okay, I mean, I must admit, I don't know exactly what the answer to this is, but the way I think about it is that I can always take a stack of NS5 brains to a stack of M5 brains, right? In the strong coupling limit, the NS5 brains go to the M5 brains. So I should have some M theory picture.
Yeah, you know, I'm just saying like the heterotic string is also there, stretched between like M9 and M9. So that's
Yeah, exactly. I mean, this is so okay, maybe this is the little string is actually the heterotic string. Once you decouple the gravity. So this is the heterotic string. So the way you can think about it is if I just get rid of all the M5 branes, right? If there's a single M5 brane, right? If you take the limit, then there's like a string from the M9 to the M5, and this same string from this M5 to the M9, right? And if this M5 wasn't there, then this would just be, as you say, the heterotic. Not sure if that helps, but yeah.
I think the confusion is I wouldn't have expected, and maybe Huri is a similar issue. I wouldn't have expected an M theory picture in the limit where you discuss little string theory. Because you've asymptotically taken G string to 0, which means you just shouldn't have a good description in terms of any kind of Java-Witten picture. It just gets collapsed. The same thing is true for type 2A, you know, M5 brains.
I think maybe this is
branch.
maybe sorry. Yeah, maybe it's because it's I mean I see what you're saying. Like the G string is 0, and then so there's no M theory circle. But
I mean, you can start from this picture and take a limit of this, but it will, I think, end up collapsing everything.
No, when you want to collapse, then it's going to be strong coupling.
I mean, collapsing is weak coupling string theory, strong coupling M theory.
yeah, yeah, the way I agree, but the way I always thought about it was just take the NS5 branes, take them to M5 branes, and the rest work it out. But
What is the flat connection at infinity? Which infinity is this?
this is the choice. So it's the choice for the connection of the E8 bundle at the boundary of C2. So C2 mod gamma G, which is S3 mod gamma G. This is an additional choice.
So this is for the case where you realize the little string theory via an ALE-like singularity.
Yeah, exactly. Yeah, this is the ADE type.
Oh, I see. Oh, I see. So what does that correspond to? What does that flat connection mean?
So this is just it's sort of you can think of it as a boundary condition for your bundle once you have this sort of C2 mod gamma G type space. So if you have a bundle over a non-compact space like this, you have this boundary choice for the connection for the E8 times E8. So you have these two choices here for each of the E8s.
I see.
But yeah, this is a good point. We should maybe I'll get back to you guys about this. Maybe.
C2 might see T-dual having n fibrations. What is it called?
Yeah,
It's in type, it is in M theory right now.
No, but this, I thought we agreed that wasn't good to be if you want to decouple gravity.
T-duality is somehow weirder, right? I've got the details, but because this thing also carries the C2 mod, whatever, carries more than, if you make it ALF, it will carry more than just KK charge.
Okay,
Because of some small instantaneous. It depends on what the gauge model is doing over it. So I think the choice of flag connection is probably specifying some total instant charge.
Okay.
And it will flip one to the other.
Cool. So yeah, let me move on and then maybe we can talk about this later. Okay, so yeah, so we have a similar story for the SO32 heterotic LST, right? Very similar, but now you of course have a choice for the SO32 bundle. In this case, however, it was shown a long time ago by Intriligator and Bloom that in this case the theory you get is actually the shape of the quiver is the affine Dynkin diagram of your singularity type here, or its foldings. So in particular, let me give you sort of a visual example in terms of if you pick the singularity, let's say to be E8. In this case, you get the following quiver, where you see the full SO32 factor here, and you see the Dynkin diagram of affine E8. And another thing to note is that here, in this case, the number of five branes, or the number of NS5 branes, is encoded in the ranks of these gauge algebra. So these go as n, whereas in the E8 times E8 theory, it was the number of strings that you had on the quiver.
Wait, sorry, I think I confused myself. So you're putting n NS5 branes on the singularity, or these are two different cases?
No, yeah, these are. I'm not yeah, I guess yeah, I am putting them on the single in the sense that yeah, this is the 6-dimensional world volume of the NS5 branes, and then they are probing the C2 mod gamma G type space. Yeah. Yeah, I mean, this is the SO32 case. The stuff on the previous page was the E8 case. So there's different NS5 branes.
Gotcha.
Yeah. Good. Right. So now that we know what heterotic LSTs are, let me sort of explain what we mean by T-dual LSTs. So before that, we need to put these theories on a circle, right? We want to look at T-duality happens in lower dimensions. We want to look at 5D theories. So if you take a 60 string theory, you put it on a circle, you get a 5D Kaluza-Klein theory in general. But if you have a discrete symmetry in your original 60 theory, then you have this additional choice that you wouldn't have if you didn't have a discrete symmetry of twisting by this discrete symmetry along the compactification circle. By which what I mean is that you have the choice of turning on a discrete holonomy for the background gauge field. So you turn on a background gauge field for your discrete symmetry, and then depending on which holonomy you pick, you get what's known as a twisted 5D theory. So in particular, the discrete symmetries we'll consider mostly are what are known as outer automorphism twists, which come from the gauge and flavor algebras in your theory. And so what you can think of these outer automorphisms as generalizations of charge conjugation that you have for, say, a U1 gauge theory. And so, for example, for E6, you have you can sort of, well, so for the simple Lie algebras, you can actually see these outer automorphisms from their Dynkin diagrams. So for E6, you have this you have the symmetry of the Dinkin diagram, which is Z2 reflection symmetry. So this is your charge conjugation symmetry in this case. And in terms of the gauge field, you essentially have this condition, which is pretty clear, which is that the fact that the gauge fields, once you turn on your gauge fields, can come back to themselves up to an action of their discrete automorphisms. And so for the simple E algebras, you have the following automorphisms. You have these Z2s, and then you have a Z3 for the SO8 because of its triality. However, this is not the complete story, because naively you may think that if you have a bunch of gauge algebras, the full automorphism is just the product of their automorphism symmetries. However, what we have in our case, in our 60 theories, we have, in addition to just the gauge algebras or just the vector multiplets, we have in addition stuff that's charged under them. So the stuff that's charged under them must also respect the symmetry action. So as we'll see later on, this actually simplifies things a lot, because what you naively may have started with, I don't know, a Z2 to the 10 discrete symmetry, it turns out to be a single Z2 because of this constraint that's there because of the matter in the spectrum, and in particular the massive matter in the spectrum, which we'll see later on. Right. So now let me sort of explain where this notion of T-duality for these theories comes from. So it turns out that the T-duality of little string theories just comes from the T-duality of the original heterotic strings. So remember, we have these 10D heterotic strings. We have the SO32, we have the E8 times E8, and you put them both on a circle, and you turn on Wilson lines, and you go on to the same point in moduli space where both the E8 times E8 and the SO32, they break to the common subalgebra, which is the SO16 times SO16, and then at that point they are T-dual theories. And so that's the T-duality from in 9D for the heterotic strings. So it's a similar, it's the same thing now for the heterotic little string theories. So we have the E8 times E8, we have the SO32. I mean, here I write their full groups, which sort of I lied to you earlier, but mostly I use the algebras. So it's the same thing. You put these theories on a circle, much like you did the 10D heterotic strings. And then you turn on the twists. You have certain choices of twists that I explained in the previous slide. And then you can also obviously turn on the Wilson lines, which break these E8 times E8 and SO32s. You can encode this sort of, schematically in these maps here. So these maps basically take you from a 60 theory to a 5D theory plus the data that you switch on. Or maybe I should have said it the other way. So 60 theory plus data to the 5D theory. And so the statement of T-duality is basically that if you do this, you get the same, and if these theories are T-dual, you must get the same 5D supersymmetric quantum field theory. I'll explain what I mean by same on the next slide. But yeah, this is the statement, and sort of more formally, it's basically the equivalence of these maps. These maps that take a 6D theory to a 5D theory. So let me sort of give you a canonical example. That's a very I think a very familiar maybe example. So you take a Volt volume theory of a stack of just n plus 1 NS5 branes, no singularity and no choice of flat connection. So in this case, the E8 times E8 theory is given here. You see, it's just the 1, 2, 2, 1 strings. There's no gauge algebras or anything. There's just these flavor symmetries. And these are T-dual, famously, to a pure SPN gauge theory on the SO32 side with some, there's matter here that transforms into the SO32. And this SPN is basically the incarnation of the SPN that Witten found all those years ago in the SO32 heterotic string, where he found that there is a non-perturbative gauge algebra at the core of the heterotic instantons. So this is the incarnation of that result, basically, in the case of the little string. Good. So now let's sort of get back to this picture. So that's one example, right? So where you have some theory on the E8, some theory on the E8 times E8 side, which is T-dual to the some theory on the SO32 side, similar to what you get for the heterotic string. However, once you turn on these twists, it turns out that the structure of this T-duality chain is much more richer. And so in particular, as I'll show you later on, once you turn on twists, you allow for, in this case, for example, you would get another T-dual theory, which would be a twisted E8 times E8 theory. So allowing for twists makes you have more T-dual theories, as I'll explain. I'll show you examples later on. Right. So far, okay, I've told you what T-duality is, but how do you find or how do you claim if theories are T-dual? So like I said, I like to think of these theories as quantum field theories with this extra property of T-duality. So you can sort of use quantum field theory principles to sort of get or at least have certain data that must match for consistent dual quantum field theories. So one, obviously, which we sort of touched upon earlier, one constraint is the moduli of the 5D theory, right? So the number of deformations that you can do to your 5D theory should, of course, match for any class of T-dual theories. And in this case, the moduli that we will talk about are the dimension, the Coulomb branch moduli. So, for example, the dimension of the Coulomb branch must match, which is sort of, I mean, I guess I can sort of explain. So you have of course, the gauge algebras from 6D. So the rank of the gauge algebras from 6D, because gauge algebras in 6D go to gauge algebras in 5D. But you also have B fields, remember, from the tensor multiplets in 6D, which you then reduce on a circle, which gives you extra U1s. So the full Coulomb branch is given here. And then you also have the choice, or sorry, you have the number of Wilson line parameters that you can turn on along your circle that, of course, must also match, because this is another sort of set of moduli of your theory. And this is given by the flavor symmetry of the theory, or the rank of the flavor symmetry. Okay, so these are maybe sort of slightly obvious invariants that you must have. But this class of invariants, which is known as the two-group symmetry, is sort of maybe not that clear, but let me sort of explain what this is. So a two-group symmetry is a mixing of a one-form symmetry, so the one-form symmetry that is inherent to the LST that I talked about earlier, and the zero-form symmetries of the theory. So in this case, it's a supersymmetric theory, so it has an R symmetry, and then it has, of course, a Poincare symmetry. So this mixing of these symmetries is what's known as a two-group symmetry. And these are classified by what are known as two-group structure constants. So you label them like kappa R for the R symmetry and then kappa P for the Poincare symmetry. The exact forms of these don't matter. But the important point is that we expect these to match. And the reason is the following. These two-group symmetries also, I mean, these two-group structure constants are also certain mixed anomalies in your 6D theory. So based on just anomaly matching, you expect any class of dual theories to have these two coefficients match. And this is why we think, I mean, it's not proven, of course, but we think that these invariants, these quantities should be an invariant for dual LSTs. And sort of in some more detail, this is sort of the this mixing between the one-form symmetry. So this is the divergence of the field strength of your one-form background B field, and then its Bianchi identity is modified in this way, which essentially encodes the mixing. And yeah, so this is the data that we expect to match in 5T, and it was actually first shown in this paper by Del Zotto and Omori that the Coulomb branch and the two-group structure constants should match. They showed this via geometric constructions in F theory. And then there was a bigger sort of classification done by Lakshya and then Michaela, Muyang, and Paul, geometrically again matching. Well, Paul, matching the Coulomb branch and then kappa R and kappa P. And then last year in our paper, we actually also showed that this must match as well. Well, not must match. These are not proven. So what we showed is that this is also an invariant of all the theories we constructed, geometrically or otherwise. And so indeed, our expectations from field theory are always consistent. And the
It is not proven, but what in your mind would it mean for these things to be proven? I'm trying to understand what you mean by that.
Yeah, I guess, yeah. I guess so. So for example, maybe this thing. So for example, there's a proof that kappa P is always so geometric. This is all geometrically. There's a proof geometrically that kappa P is always 2 for heterotic LSTs. So I would like something like that for all geometries that correspond to LSTs for all these other quantities. That's, I guess, one thing. So for kappa P, it's very simple that you can show it that any Calabi-Yau threefold, I mean, I'll talk about this a bit in the next slide, but any Calabi-Yau threefold with this base type P1 times C would always have any blowups that you do along the base, so any strings you add would always keep kappa P equals 2. So something like that, I would say.
I think some other unknowns like SU2 left, SU2 right.
Oh, this is this is the SU2 right, R symmetry.
This is the SU2I, I guess.
Yeah.
Right.
Yeah. Sorry, this is SU2R. Yeah.
What happens to the other levels under T-duality?
Sorry?
What happens to the other levels under T-duality?
Other levels? What do you mean by levels?
Like the rest of the anomalies.
Oh, you mean the rest of the mixed? So yeah. So okay, let me maybe make this a bit clear. So these are mixed anomalies between the R symmetry and the gate symmetries of the theory. Yeah. And this is the mixed one between the Poincare and the gate symmetry. And your question, I guess, is about what about the other flavor symmetries, right?
Yeah.
Yeah. So the other flavor symmetries they were conjectured to also match, like the anomalies associated to them were conjectured to also match, but we weren't able to actually ever show that they match for these theories. And it's a very, very simple argument as to why I don't even think it makes sense to ask that question, because the kappa F, which is this anomaly associated to the flavor symmetry, you can have different numbers of kappa Fs in two dual theories. So you can have 3 flavor factors here, and maybe you can have 2. So how do you do the match between them?
You're just telling that basically the central charges that match.
Sorry, I don't understand that. You're saying that the global symmetry of dual theories can be different?
No. The global symmetries can be the same. It's this
can be the same. I would have said must be the same. Yeah.
Yeah. So when you say, you mean the rank, right?
The rank, not the gauge group.
The global symmetry I'm talking about.
Yeah. I mean
flavor symmetry now.
Yeah. Exactly. Yeah. The rank of the flavor symmetry is what you mean, right?
Not just the rank, the group.
No, the group does not need to match.
Why does it match?
What do you mean? If you have 2 dual theories, certainly in quantum field theory, if you have 2 dual theories, the flavor symmetry matches across the duality.
S-duality, for example, doesn't. If you have like SU3, SCFT, and you flip the diagram, you get SU2 times SU2 and the flavor.
No, that's gauge.
You're talking about the gauge symmetry.
No, but the flavor symmetry changes also.
The flavor cannot change.
The flavor symmetry cannot change in a duality of field theories.
Well, the point is this is a 5D duality, so they match the 5D rank matches. There's nothing. I'm not saying nothing about matching anything in 6D. So the 6D theories are not. I mean, they don't have the same flavor symmetry, and they sometimes don't even have the same flavor rank. But when to
No,
put
I
it on
think there is a confusion here. If there are dual theories, they surely have the same flavor symmetry. I think maybe what is being confused is
Oh, that's
whether
right.
the flavor symmetry that you're talking about survives to the 6 dimensions, or whether it is an accident of being on the tensor branch. Is that what is happening here? I'm a bit confused
Okay,
about
good,
how.
good. No, okay, no, I see. Okay, now I see your point. I see your point. Okay, so whatever I'm saying is on the tensor branch. So I'm not sure if all of this goes through once you go to the LST point. Because I mean, I think this is also in. Am I talking to Clay?
Yeah,
Okay, good. So I think this is also in your paper where you talk about this, that the fact that the two group symmetry is it doesn't have to be a symmetry of the full LST at the UV point. It may be an accidental symmetry in the IR. So in that case, you can't even match two group, right? If let's say it's not a symmetry of the UV point. So yeah, everything I'm saying is on the tensor branch. Yeah, maybe when I show you explicit examples, maybe it'll become.
yeah, no, I'm with you now. I just think, yeah, we should distinguish like matching at low energies, flavor symmetries that appear at low energies on the moduli space, which that need not work because those symmetries might not be actual symmetries of the fixed point. We should distinguish that from matching the symmetries of the actual fixed points, which
Yeah.
actually do have to match.
Right. Yeah. Yeah. Okay. Maybe we should also. Yeah. Maybe I'll maybe.
I mean, in fact, you could turn the logic around. You could say, if you find something that doesn't match that's there on the tensor branch, you could use that as information about needing either an enhancement or reduction of symmetry when you're back at the origin of moduli space.
Yeah. Maybe. Yeah. We should talk about this. Yeah, definitely. Thank you. Good. So yeah, so the goal of this work was to sort of, so like I said, yeah, these were matched for the untwisted theories in these papers. And the main goal of this work was one of the main goals was to see if this continues to match when you allow for these twists. I mean, again, field theoretically, you expect all of this to be true, but we wanted to do this explicitly and see if maybe we can find other duals that you wouldn't see if you only considered untwisted theories. Another interesting point is that kappa p, like I sort of mentioned, is true for heterotic LSTs. It's known to be true for heterotic LSTs. And there's another kind of minimal LST, which I haven't talked about in this talk, but for that theory, these type 2 LSTs, you have kappa p equals 0. And the interpretation that was given to these values in this paper by Del Zotto and Omori was that these count the number of M9 branes, which, I mean, on a sample size of 2, it makes sense, right? But then the question arises, can there be LSTs with kappa p equals 1, right? A single M9 brane. And hopefully by the end of this talk, I will convince you that these theories do exist, and in particular, these are a type of twisted LST. Good. So, right.
Is there a reason to think outside of the string theory evidence? Is there any reason to think kappa p couldn't be bigger than 2?
Good. No, I don't think so. I don't think outside of string theory evidence there is any reason. No. Yeah, but
CHL-like. Maybe something like CHL, but LST type.
sorry.
So,
Yeah, it's blue.
Yeah, I mean, if it counts the number of M9 branes, then it can't be. But like you say, it's if it's not from string theory, then who knows?
Well, I guess you can count how many E8s you can have. Like how many global gates. So the central charge, like this kappa.
Oh, right. Good.
Gives you bounds the left moving central charge.
Yes.
But if it is smaller, like you already know that you cannot fit in enough current algebras.
oh,
That's a good point. That's a good point. But I mean, it could be that I mean, you don't. Yeah. I mean, I guess the question then is that, are you saying that if kappa p is really the constant number of M9 branes? If it doesn't, then I mean, there's no reason to expect that kappa p should only have contributions from the E8s. And it could be that you have some weird 60 theory where kappa p.
The maximum, how many at most you can fit.
Yeah, I mean, potentially. I mean, I would tend to agree with that. Yeah, there is, as you say, a bound from the current algebra of the world sheets of the non-critical strings in the theory, which is maybe you can use that to just fix kappa p to something. Yeah, that's a yeah. I mean, there are probably bounds there. I would have to check, but yeah, good point. Cool. So right. So far, okay. I've said that sort of the data that I've showed you on the previous page is sort of known to only be necessary for two duality, and there's no sort of proof yet, in the way I think at least, that this is it's sufficient. And so to sort of counteract this, we use this what Aspinwall Morrison did many years ago now. How they showed that the SO32 and the E8 times E8 theories are T-dual, and they used F theory. And we'll basically use the same techniques, but now apply to little string theories. I mean, I won't talk about the geometry beyond this slide, but if people want to talk or have questions about this, I can talk at the end of the chat because end of the talk, because this would be a talk on its own. So essentially what the point is that you construct 60 quantum field theories in F theory by putting F theory on some non-compact Calabi-Yau threefold, right? F theory is a 12-dimensional theory. You put them on a 6-dimensional manifold, you get a 6-dimensional theory. And so the idea of T-duality is that if this Calabi-Yau admits more than one elliptic fibration structure, right? So you need an elliptic fibration, but let's say there's many elliptic fibrations that you can pick within the same Calabi-Yau, then Aspinwall Morrison basically showed that sort of these are T-dual. And you can show this via FM theory duality. And so we use the same thing. We use the same techniques. We construct these Calabi-Yaus explicitly. And for every sort of field theory argument, for every class of T-duals that we write down using these field theory arguments, we try to construct a Calabi-Yau realization just to cross-check our results, and it always matches. And all the data that I showed you previously is just some geometric data now, which always matches, and it's a nice cross-check. And for the twisted theories, there's a slight twist that you can also allow for genus-one fibered Calabi-Yaus, not just elliptically fibered. And so we use this, and we sort of use a cross-check on our T-duality chains, which I'll show you now in just a bit. But yeah, if people have more questions about the geometry, I'm happy to talk.
So the genus-one fiber cases have no sections in general.
Yeah, exactly. Yeah, no sections. So there we're essentially constructing directly in M theory, right? Because F theory requires a elliptic fibration. So here we just construct them directly in M theory and then do a field theory uplift of our twisted theories, which always works. Good. So right now, basically, I'm at the results portion of the talk. And so before we get into that, let me sort of recalibrate everyone. Right. So what we do is we will use this T-duality invariant data that's conjectured to always match for T-dual theories, and we'll predict a new set of duality chains but now we will include these twisted little string theories. We'll use the geometric construction as a cross-check, as I just mentioned. One important thing that I'll show is in an explicit example is how the massive spectrum of your theory actually determines what are the actual symmetries of your theory, which is why we have to keep everything, so we don't integrate out anything, because if you didn't know about this massive spectrum, we wouldn't know what the actual discrete symmetry of the theory is. And then I will use this T-duality invariant data to predict a new class of LSTs with kappa p equals 1. And I say predict because, as I'll show you, we don't have the geometric realizations of these. So we don't have the cross-check, but we have everything else. Good. All right. So now let's get into this, how we constructed these theories. So as I said, this invariant data is very powerful. We can use this to find T-dual theories. So what we do is, so let's start from some heterotic LST with some singularity G and some number of 5 branes. Now I'm just saying 5 branes, it could be M5 branes or NS5, it doesn't matter. And in this case, you can show that the dimension of the Coulomb branch here and kappa r are always these linear functions in M, in the number of fibranes, where C2 and R2, these coefficients, are fixed by the singularity. So this bit is fixed by the singularity and the number of fibranes. And then these constant pieces, C1 and R1, are actually fixed by your choice of flat connection. So they're fixed by your flavor symmetry. And so the strategy we use is that we want to match, we want to have T-duals in families of M. And this is what's always worked in the cases of, for example, untwisted theories. So what I mean by that is I have two classes of T-dual theories for any value of M. M large enough. So for small M, there's sometimes some issues, which I won't get into. So the strategy we use is then the following. We say that if I take an LST with some coefficients C2 and R2 and some number of fibranes, M, and I take another LST with some other coefficients, C2 tilde and R2 tilde, and I pick some other number of fibranes, M tilde, such that these always match. I mean, there's some relation between M and M tilde such that this always matches. And then beyond that, we obviously need to match the full data. Beyond that, we can then check, once this M-dependent piece is matched, we can check that, oh, can we always pick a flat connection such that the constant pieces match as well? Because this is a very basic, very low-level necessary condition. And it turns out it's very powerful, and we can always match stuff using this. So C2 and R2 are given by these group theory coefficients here for untwisted theories. And for twisted theories, we actually determined these in our paper via some field theory. And then a consequence of that was that we can see that kappa R and kappa P are actually not modified under outer automorphism twist. Well, kappa P makes sense. It's something that depends only on the base, so it doesn't matter. But kappa R also doesn't change under outer automorphism twists. And so this R2 doesn't change if you twist the algebra or not, or to twist the theory or not. Whereas, so the Coulomb branch, of course, changes when you twist your theory, because it's an identification of the roots of your gauge algebra. So you're of course reducing the rank of your gauge algebra. And so this is indeed the strategy we use to find dual theories, and it turns out this works very well, and we have a bunch of new duality chains in our paper. But now I'll present you an example of one of the more interesting ones, because we had explicit geometric realizations of these as well. So here, so to match, so if I just start with this assumption that I want to match these leading M pieces, then one can actually write down immediately a duality between untwisted and twisted E8 times E8 theories, E8 times E8 LSTs. For the following singularity, so G prime is the untwisted singularity, and G to the N is the nth order twist of your algebra. And so this is the sort of result we find, where this twisted LST is dual to this untwisted LST, as long as the number of fibranes on both sides are related through the order of the twist. We don't know why this condition must be there, but this is what we always find. And furthermore, it would also be interesting to see if there's like a group theory there's a group theory version of this table. If there's some relation between these algebras beyond just this matching of the leading M piece in some physics problem that we have. And so just based on this, so I've done nothing more yet. Just based on this, we can write down the following duality chain. So this is the twisted E8 theory. This is the untwisted E8 theory. And then these are the SO32 theories that you just expect from the usual untwisted normal T-duality, right? And so we can always write these down. And it turns out we can always choose a flat connection such that in addition to the M piece, the constant pieces always match. And then finally, as a final check, we also explicitly realize these geometries, or these geometries in F theory. And so indeed, just matching the M piece was enough for us to find these twisted T-duals, twisted T-dual LSTs. And this is just one example of a duality change. We have other cases as well, but this was sort of the most easily realized geometrically. Good. So now let me finally show you an explicit example of this duality. So now I can start with n M5 branes probing an E6 singularity. So in this case, the full tensor branch of the theory, okay, I should have said something else. So I pick an E6 singularity, and I also pick some flat connection such that the full E8 is broken. So it's broken to E7 times U1 on both sides, as you can tell. And this is the full. Yeah.
5 to 10 more minutes.
Yeah. Cool. Sorry, yeah, I didn't realize. Yeah, 5 to 10 more minutes is fine. Yeah, I'll just speed up now. Good. So this is the theory we get, and in this case, you can see that if naively I just think of these algebras here, then there's an autoautomorphism associated to each of the E6 and SU3s, right? Because both of these algebras have a Z2, and so there would be an autoautomorphism associated to each of them. However, as I said, there's some spectrum in the theory that constrains this. And in this case, it's this E string, this empty one curve, or no, I shouldn't say curve. I didn't introduce geometry. It's the empty one node. And the matter associated, or this is sort of like massive matter on the tensor branch, because the string is tensionful, is in representations of SU3 plus X plus E6. And in particular, the matter is given here. And in this case, you can see that if I just twist by the E6, for example, just one E6, right? What I would have to do in that case, the action on the matter is such that I would have to flip the 27 and the 27 bar around. Now, of course, this is not a symmetry of the theory, right? The matter is changing. So the idea is you have to twist by both E6 and SU3, because if you then flip the 3 and 3 bar around, then your theory is fine. But as you can then sort of follow that, you have to twist all of these. You can't just twist E6 and SU3, because the moment you twist SU3, you also have to twist this E6. And so at the end of the day, there's a single Z2 symmetry of your theory, which is also nice because we don't expect discrete symmetries from these geometric constructions to be we don't expect Z2 to the 10, for example. Calabi-Yaus that realize Z2 to the 10 a discrete symmetry. So there should be very small amounts of discrete symmetries. But there's a single Z2 twist that you can do, and you can do this twist, and you can get this theory right here, where you see that the U1 is also gone, which again is a similar argument to the one I made here. But it's important it's very subtle, because you need to know if the U1's there or not, because we want to match to dual theories, and the flavor must match for T-dual theory. So if the U1's there, it would of course affect the flavor. But in this case, it shouldn't be there. And then you can, the sort of table I showed you earlier, it predicts that there should be an untwisted E7 type E8 times E8 theory. And so in particular, with some work, you can write it down explicitly, which I do here. And you can show that this theory is indeed dual to the previous one for the following, for this relation between the number of 5 branes. And of course, when I say dual, I mean, at this point, I just match the entire data that I talked about, the T-duality invariant data. But then we also constructed the geometries explicitly, which realized these theories as, inequivalent elliptic fibrations, or genus-one fibrations. Good. So yeah, one thing, I mean, this, we don't have to talk that this we can skip because we're running out of time. So cool. So, so let's consider now this new class of LSTs that I was talking about. So recall that there's another kind of symmetry that one can have in your 60 theories, which is associated to the permutation of the tensor multiplets of your 60 theory here, which you can clearly see is a symmetry of the theory. So you can then choose to twist by this theory, which is what I call here tensor twists. And so when you put this theory on a circle, you twist by it. No, this is not an LST, and this is just some 60 theory. But you can of course see how this might be true for any 60 theory. So if we take such LSTs where this is a symmetry, we can take in this case the twist would of course affect the Dirac pairing matrix as well, because the Dirac pairing matrix encodes information about these tensor multiplets, and if you're twisting by them, then of course the 5D Dirac pairing matrix, which is given here, would be something different. It can be modified. And so unlike the case where I had just outer automorphism twists, I can now do these twists, which lead to what are known as twisted two-group structure constants. And because now in this case, these kappa P and kappa R can change, in particular because the Dirac pairing matrix can change. And so these are these new, I've just written these in this new notation where you can sort of see these show up. Good. So now we get what are known as, we can construct what we call CHL-like twisted LSTs, as, I mean, the name you'll probably realize why we call it this. So you start, let me like show you this, we had an explicit example. We take two M5 branes probing some E6 singularity. You get the following theory. You see these two E8s unbroken at the end. And you see that your quiver has a symmetry, which is a Z2 reflection symmetry about this SU3 factor. And so you can twist by it. Once you twist by it, you see that the resulting theory, and you compute the relevant data, you find that the resulting theory has kappa P equals 1, which is what we set out to do. And sort of there's an intuitive reason why you can see why this happens, because you see that you're identifying the two E8s, right? And so effectively what you're doing is you have now a single M9 brane in your theory, and this is then consistent with the interpretation that this value counts the number of M9 branes. You can do the same thing now with, we can also write down a similar T-dual. So this, I can write down a T-dual tensor twisted SO32 theory to the one on the previous page, which of course then also comes from this sort of tensor twist. So you can again see that this is a symmetric theory where now the fixed nodes are one in these guys instead of just one curve or one node. And once you twist and you compute the relevant data, you find that indeed at the level of the matching data, at least, these theories are T-dual. And in our paper, we basically write down a bunch of these kappa P equals 1 type theories. There's actually a very finite number of them on the SO32 side, because there's a very finite number of quivers on the SO32 side that have a discrete symmetry to begin with. So yeah, but we obviously, as I sort of mentioned earlier, we don't have geometric realizations of these theories, which would be an interesting check to do beyond just the matching of this data. I mean, so far it hasn't been wrong, but it would still be very interesting to do. Cool. So now let me get to the outlook and just reiterate the results and maybe some future directions. So the goal was to, extend the T-duality landscape of heterotic LSTs by explicitly matching the duality invariant data, and particularly in the case where you allow for these twists. And then once you have these based on the duality data, you can then try to go into the geometry, go into the F theory, and try to prove our duality chains prove the duality chains that we predict from field theory. And then finally, we also gave evidence for the existence of this novel class of LSTs with kappa P equals 1. So now we have some stuff that, I mean, there's a lot of stuff one can do, but some of the stuff that I'm interested in is, so obviously to get the geometric constructions for these kappa P equals 1 type theories. This is, I mean, I didn't refer to this too much, but sort of there's a construction of LSTs. There's a way to construct LSTs in terms of two kinds of SCFTs. So namely for the experts, the Orbi instanton theories and the conformal matter theories. And so what one can actually use the LSTs to study its components. So the SCFT components. And so we're working with Florent and Paul to sort of see what the implications for this is in particular for the Higgs branches of the SCFTs. Then there's also another interesting thing that one can ask regarding the T-duality landscape of the full 60 supergravity theory, right? Because there's an argument that it's a very simple argument that every 60 supergravity theory with at least one tensor multiplet has a heterotic string description. And of course, if you have a heterotic string description, and if you decouple gravity, you then get a heterotic little string description. So what sort of the question is what percentage, I guess, of the T-dualities of the little string theories uplift to the full 60 supergravity theory? Can we always find a representative in the LST case that is also
Not true that there's always heterotic.
Sorry?
Not always true.
No, I agree. It's not always true, because I mean, one way that you can see this is you can't just increase M, right? The number of fibranes. So I can't have.
No, I'm saying that for T greater than 0, there's always a heterotic string.
Oh.
There are examples with that.
Um.
Like if theory with an Enrique space doesn't have. The two antifold.
So I thought, I mean, the way, I mean, you can, yeah, the way I thought about, the way I understood it was that you always have a P1 in your F theory description.
You don't. That's the point.
Okay.
If you, for T equals 9, you also have an Enriquez surface.
Maybe
Enriquez
let me finish.
Okay, I see. Good. Yeah, maybe we should talk about, yeah. I read this in Timo's paper, but maybe it's cool. So yeah, the thing to then study would be that what part of the 60 supergravity T-duality landscape the LSTs cover, or the LST T-dualities cover. Then finally, we have some work going on with Christian, who's a Chicago PhD student at some point, which is regarding this relation that was, I think, studied in these two papers between LSTs and LSTs on a T4, more specifically, and TT bar deformed CFTs, and to basically see what is the sort of the signature of these higher form symmetries of LSTs in these theories, and in particular in their bulk duals. So yeah, LSTs have bulk duals, and what is the realization of that in that case? Cool. Thank you for your attention. Hello, sorry.
Are there any other questions?
We will have to leave very soon because of another seminar. One quick question for you. And then maybe we can have discussions offline after.
Yeah.
Just in 60, the determinant condition you gave in the beginning, with classifying the cases as SCFT, little string theory, and gravity, does that have a bulk interpretation already in 60?
Oh, good. Yeah. So, well, 60 SCFTs, for example, are, you know, their bulk description is conjectured to be this near horizon limit of the M5 brane.
That would be, in that case, it would be ADS7, right? You go up to ADS7 cross S4, but the interesting thing is the LST is the asymptotically linear dilettante background.
Yes.
Which somehow is determinant equals 0. And I'm wondering how one can tell, like, it'd be nice, do you have explicit cases with determinant -1 that one can play with?
But determinant -1. Oh, yeah. I mean, we have the geometries. Like, we always decouple. So the way we start is from a compact geometry. So we have the supergravity theory, and then we decouple it. So yeah,
is there a brane picture with determinant -1, or only a geometry that with a local singularity?
So 60 supergravities are in I think we only have them via F theory, but there should be a brane picture. I mean, one could probably
I think if there were a case with a brane picture, it would be useful.
there are.
There is a brane picture with determinant -1. And 5. Say it again.
Hojava Witten wall, don't decouple gravity, would have two M5 branes.
On the wall itself?
I mean, then you want to shrink it to go to the heterotic limit, but if you don't shrink it, then you just keep gravity dynamical, then the total theory will have.
Oh, so you say in heterotic.
Yeah, because
Should
between M5 branes, sorry, you get like a -2 curve. The boundaries are like 1 curves, the one stretch between everything is the heterotic.
Uh-huh,
Yeah.
okay.
If you just put 1, then you just get the F1 vis, which has a perturbative heterotic description.
Yeah, F1 is that. Yeah, exactly. Yeah, good.
Okay, very good. Okay.
Thank our speaker again.
Okay,
Yeah.
thank you.
Thanks a lot.
Sorry, we have to rush out. There's another seminar.
Yeah.
Sorry.
Right now. So,
Sorry.
um,
Thank you.
Thank you guys.